be a string, right? Or it could be a more complex value, like a struct, right? So a struct can have multiple fields of different types in them, and we can sort those as well, right? And as I mentioned before, we sort the items based on a key, right? And the key could be, it's possible that the key could be the entire item, right? So if our items are just integers, then the key would just be the integer, right? If the items are structs, then we might sort by one of the fields in that struct. Okay, so all right. So here is an example of sorting. So here we basically have an array of structs, right? And the structs represent students. Okay, so each student has an ID and a name, and we can sort by two different things, right? We could sort by the ID, right? In which case the key would be the ID. Right? And notice that this array here is sorted by ID, or we could sort by name, right? And that means the key would be the name, right? So here, notice that the array is sorted by name, and just notice that we have two students with the same name, right? So we need to be careful about these, like the ordering of these two structs, right? And the sorting algorithm that we use might determine what order these appear in our final result. Okay, so when we sort, so the sorting algorithms that we cover over these next few lectures, they'll always be taking in an array and a low and a high, right? So the low is the index of the leftmost element that's being sorted, right? And high is the index of the rightmost item that's being sorted. So we're always concerned with sorting a slice of the array, okay? And often you want to actually sort the entire array. So if you want to sort an entire array of size n, then you would just let low be equal to 0 and high be equal to n minus 1, okay? All right, so more formally, what does it mean to sort, right? So first of all, we have an array of items, right? And low and high are valid indices, right, on A. So low and high have to be between 0 and n minus 1, and low has to be less than or equal to high, not less than, not just less than. Okay, and after we run the sorting algorithm, the values between indexes low and high, well, they have to contain the same values as before the sort, and they have to be ordered, right? So that's what this is showing. So the item at index low has to be less than or equal to the item at index low plus 1, and so on, all the way up to index high. Okay. So there are also some properties that we want to examine, right? So for all the algorithms, we want to examine the time complexities, but also for sorting algorithms, there are some extra properties that we're concerned with. One of them is stability. We also have adaptability and in place, and we'll have a look at each of those. Okay, so first, stability. So what does it mean for a sort to be stable? So a stable sort is a sort that preserves the relative order of items with equal keys. All right, so keys I described earlier, right? If we're sorting an array of structs, then we might sort by one of the fields in struct, and that field would be the key, right? And here's like the formal definition. So if we have a stable sort, then for all pairs of items x and y, where the keys are the same, right? If x came before y, so x precedes y in the original array, then x should precede y in the sorted array. Right? If you're not sure about that, I have some examples. Okay, so Here I have an array of playing cards, right? And each playing card has a value and a suit, right? So notice that in this array, I have a couple of cards with the same value, right? So I have 2 6s and I have 2 4s, right? Now, if I do a stable sort on the value, right, then the 2 of clubs should appear, sorry, 2 of spades should appear first, right? Because that's the card with the smallest value. Right, now, the next highest value is 4, right? But we have 2 4s, 4 of diamonds and a 4 of spades. Right? But because in the original array, the 4 of diamonds appears first, it should also appear first in the final array. Right? So 4 of diamonds, then 4 of spades. Then we have 5 of hearts. Right? Then we have 2 6s, but because the sort is stable, the 6 of clubs should appear first, then the 6 of hearts. Okay? So that's an example of a stable sort. But here's an example of an unstable sort. Right, so we have the same cards as before, and we can see that the 4s have remained in the same order, right? But the 6s are not in the same order as before we ran this sorting algorithm. Right, so that's just one example of an unstable sort. Right? You could imagine that there's another example where we switch the 4 around, right? Or we switched both the 4s and the 6s around. So with an unstable sort, in general, you can have multiple results, right? But if you use a stable sort, there is only one possible result. Right? Okay. So why do we care about stability? So when is stability important? Well, sometimes we might want to sort the same array multiple times on different keys, right? And there are some sorting algorithms that rely on this, which we'll look at later, such as radix sort. But for now, I've got an example here where suppose we have an array of first names and last names, right? And my goal is to sort the array such that the first names are in alphabetical order, right? But if we have two items with the same first name, or 2 people with the same first name, then their last names should be in order, right? So for example, here we have 2 Alices, right? So what I want is for Alice Hatter, right, to appear before Alice Wonder, right? So one way we can do that is to first sort by the last name, right, and then sort by the first name using a stable sort, right? So what happens when we sort by last name? Then all the people will be ordered by last name, right? Quite obvious. So we have Andrew Bennett first, then we have Alice Hatter, then Jake Renzella, and so on. Right, so that's not quite what we want, but now let's sort by the first name using a stable sort, right? So if we sort by the first name, then the Alices will appear first, right? And because we're using a stable sort, right, Alice Hatter will appear first, right? And then Alice Wonder, right? And for the Andrews, Andrew Bennett will appear first, and then Andrew Taylor, right? So if we use a stable sort to sort the first names, right, then we get what we want, right? So the array is sorted by first name. If 2 people have the same first name, then they're sorted by last name, right? But the problem is if we didn't use a stable sort when we were sorting by first name, right, then it might be possible that, you know, the Andrews might not be in the same order as after we sorted by last name, right? So, for example, Andrew Taylor might end up appearing before Andrew Bennett, right? And then we wouldn't get the result that we want. Right, so that's just an example of where stability might matter. Okay, so when does stability not matter? So one example is when all the items in the array have unique keys, right? So for example, if we go back to that student example from earlier where each student had a ID and a name, right? We know that the IDs are unique, right? So if the keys are guaranteed to be unique, then stability doesn't matter. Right? Another situation where it doesn't matter is if the key is the entire item, right? If you're sorting an array of just integers, so just raw integers, then it doesn't matter if the algorithm is stable or not, right? Because if you have duplicates, there's no way to tell if the duplicates have swapped because they look the same, right? Okay, so it's for stability. So another property is adaptability, right? So what is an adaptive algorithm? So an adaptive sorting algorithm takes advantage of existing order in its input, right? So for example, an adaptive sorting algorithm might perform better, faster, if the given input is sorted, as opposed to if it's random or reverse sorted. They can be quite common. All right, and the last property that we want to consider is in-place sorting algorithms. Okay, so what does it mean for sorting algorithm to be in place? That means it does the sorting within the original array, right? And it doesn't use any temporary arrays. Okay, so this can be important if you have memory constraints or if you have a large number of items, right? So let's suppose you're sorting 10 million items, right? If your sorting algorithm requires a temporary array, that means you have to allocate space for 10 million items, right? And you might not be able to do that depending on your storage or memory requirements. Okay, so now what are some of the things that we're going to have in our code if we implement these sorting algorithms? So first of all, we have a typedef here. And if you haven't seen typedef before, typedef is a way we give a type a new name, right? So here I'm saying typedef in item. That means I'm giving int a new name, which is item, right? And the reason we might want to do this is because we might want to swap this int out for a different type, right? And this makes it easier for us to modify our code in order to sort different types of items, right? And we also have some hash defines here. So these are actually macros, right, which is a hash define, sort of like a hash defined function, right? And we can also use these to easily swap out different types, right, in order to sort different types. Okay, so this is just an example where we are sorting integers. Okay, so here's an example where we are sorting enrollments, right? So each enrollment has a name and a course, right? And since names and courses are strings, the way we compare them is to use strcomp, right? So you can see that in the above example here, the item was just an int, right? So the key is just the entire item, right? But when we're dealing with structs, then the key is one of the fields in the struct, right? So if we're sorting by name, the name of the student, then the key would be a.name, right? And to compare, we would use strcomp, right? Because names are strings. All right, so how do we analyze sorting algorithms? So since in our sorting algorithm functions, they take in a low, which is the index of the leftmost item, and high, the index of the rightmost item, the number of items that are being sorted overall is high minus low plus 1. All right, and we would typically just write n for that. Okay, and we also have some very common operations that occur in sorting algorithms, which we might count. For example, C is the number of comparisons between items, right? And we'll use S to indicate the number of times items are swapped. Okay? And the aim is usually to minimize the number of comparisons and the number of swaps. All right, so also when we're analyzing sorting algorithms, some common cases that we like to consider are random order. Right, so random order typically gives us, the random, the average case analysis, right? Because you're just using a randomly sorted array, and that will give you the average case. Sorted, so it's also useful to test how the algorithm performs on sorted order, because if the algorithm is adaptive, then it'll be more efficient when you give it a sorted array. Right? Reverse sorted order is also a good input to test. Right? Reverse sorted order can be a worst case for some algorithms. So we will have a look at that. Okay, so here are just some examples of sorting algorithms. Right, so we have some algorithms which are kind of inefficient. So selection sort, bubble sort, insertion sort, and shell sort. And we also have some more efficient algorithms like merge sort and quick sort, which we'll look at later this week. All right. And we also have some non-comparison based sorting algorithms. So the thing about this first two groups of algorithms is that they are comparison based, which is that they rely fully on comparing pairs of items, right, in order to sort items. Right. Some sorting algorithms need a bit more than that, and some examples of that are radix sort and key indexed counting sort. All right, so first of all, we're going to look at selection sort. All right, so selection sort is a really simple method. It's kind of brute force-ish. So how it works is we find the smallest element in the array by looping through it, and then we swap the smallest element with the first element in the array. All right? Then we find the second smallest element, and then swap it with the second element in the array. Then we find the third smallest element, swap it with the third element, and so on, all the way up to the end, where we find the second largest element and swap it with the second last element. Okay, and each iteration of selection sort improves the sortedness of the array by one element. And I have some diagrams coming up to show that. Okay, so here's an example. So we want to sort this array using selection sort. Right, so first of all, we find the smallest element, which is 1. Then we swap it with the first element, which is 4. Right? So we swap it. Then we find the second smallest element, which is 2. And we swap it with the second element, which is 4. Right? Then we find the third smallest element, which is 3. Swap it with the third element, which is 7. And so on. Right? So the fourth smallest element is 4. We swap with the 7. The fifth smallest element is the 5, so we swap it with the 8. Right? The next smallest element is the 6, and the 6 is actually already where it needs to be, but if we swap it with itself, that doesn't matter, so we do that. Then we find the next smallest element, which is 7, and we swap it with the 8, and then we're done. All right, so when I said each iteration improves the sortedness of the array by 1. That's what I mean, right? So the sorted part of the array is gradually growing every time we find the next smallest element and swap it. All right, so here is the implementation of selection sort. Right, so we have an outer loop here that iterates from low up to high -1, right? And inside the for loop, we are basically finding the next smallest element, right? So we keep track of the index of the minimum elements, right? So we set min to I initially, then we loop through the rest of the array to find the minimum element. Right? So if we find an element index j, which is less than the minimum element that we found so far, then we update min. Right? And at the end of the iteration, we swap the element at index I with the element at index min. Right? Okay, so let's analyze the algorithm. So how many comparisons and how many swaps do we do? Well, in the first iteration, right, we make n-1 comparisons. Right? That's because we take the first element as the min, then we compare it to the other elements until we find an element that's smaller, then we update. Right? And in the first iteration, we make one swap. Right? Then in the second iteration, we need to find the second smallest element. That takes n-2 comparisons. Then we perform a swap at the end, and so on. Right? So if we count out how many comparisons there are in total, there are n-1 plus n-2 plus blah, 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 plus 1. Right? And that sums up to this expression here. So n times n-1, all divided by 2. Right? And this implies that our algorithm is O of n squared. Okay? The number of swaps is n-1, but that is much less compared to the number of comparisons. Right? So the number of comparisons here determines the time complexity. All right, and another thing to notice is that the cost is going to be the same regardless of how sorted the original array is, right? Because selection sort, it just finds the smallest element, then it finds the second smallest element, and so on. It doesn't matter if the array is sorted or not. Okay, so let's talk about the properties of selection sort. So first of all, selection sort is unstable. Okay, and the reason it's unstable is because it performs swaps between items that are far apart from each other. Right? It performs long-range swaps, and I have a really minimal example here. Right? Suppose we have this array where each item has a number and a letter. Right, so we have 2a, 2b, 1a, right? Sorry? It's not hexadecimal, they're just two separate things. So it's just a number and a letter. Oh, so yeah, so just imagine that it's a struct containing a number and a letter. Right, so the number is 2, the letter is a. Yeah, so 2a isn't a number, it's just a letter. Oh, it's a number and a letter. All right, so once we find the smallest element, right, so we're sorting by number here. So once we find the smallest item and swap it with the first item, right, which is 2a, the 2's have swapped places, right? And when the algorithm finishes, the array is going to look like this, right, which means that the sort was unstable. All right, so as for the other properties, right, selection sort is non-adaptive. Right, I sort of explained that earlier because it does the same thing regardless of how the original array is sorted. And selection sort is in place, right, which means it sorts within the original array, doesn't use any temporary arrays. All right, so that is selection sort. Do we have any questions about selection sort? Yeah. Sorry, can you speak up a little bit?
You mentioned that the cost of the selection sort remains the same.
Yeah.
Does it mean like if it's already in the scratch places, it's gonna still try and swap it? Or isn't it just move across the next smallest and just have it remain in the same place?
So, right, so if our array is sorted already, selection sort, it still performs the same steps. So it doesn't really have a smart way of detecting whether the array is sorted already. It still goes through the entire array, finds the smallest element, then swaps it, and then so on. Yeah. Okay, so if we don't have any questions, let's move on to bubble sort. All right, so bubble sort. So how does it work? So bubble sort makes multiple passes from left to right. So left is low, and right is all the way up to high. And on each pass, we swap. So we compare adjacent elements, right? And we swap any of the pairs that are out of order. All right, and I'll show you an example of that later. So what ends up happening is that elements bubble up the array until they meet a larger element, right? And that's why it's called bubble sort, because elements bubble up the array. Right? And we stop if there are no swaps made during a pass, right? So if we make one pass down the array and we don't make any swaps, that means the array must be sorted, right? So we can stop. All right, so here's an example. So suppose we're sorting this array, right? So what's going to happen during the first pass? So during the first pass, we're making a pass from left to right, right? So we're comparing 4 and 3, and since 4 and 3 are out of order, we're going to swap them, right? So now it's 3 and 4. Then we compare 4 and 6, right? 4 and 6 are ordered, so we leave them as they are. Then we compare 6 and 1. 6 and 1 are out of order, so we swap them. Then we compare 6 and 2. 6 and 2 are out of order, so we swap them. Then we compare 6 and 5. And 6 and 5 are out of order, so we swap them. Right? So the result of the first pass is that the largest element is brought to the end of the array. Right? So since we know that the largest element is now in its proper place, the next passes don't need to go all the way up to the end, right? It only needs to go up to index high minus 1, right? Right, so here's the second pass. Right, so we compare 3 and 4. 3 and 4 are ordered, so we leave them alone. Then we compare 4 and 1. 4 and 1 are out of order, so we swap them. Then we compare 4 and 2. 4 and 2 are out of order, so we swap them. Then we compare 4 and 5, and 4 and 5 are ordered, so we leave them alone. And the result of the second pass is that the second largest item is brought to the end. Okay? Yeah?
How do you tell that 5 and 6 are already the largest item, then we don't need to care about them anymore? I mean, how does the computer know this?
Well, the computer doesn't know it, but we know it. So we.
How do we know that they are the largest one? Although we only have 6 integers, so we can count it and find it out.
Yeah.
How do you prove this situation?
Right. Yeah. So suppose, right. So the question is, how do we prove that the largest element ends up at the end, right?
How do you
Yeah.
show that this is the largest?
Yeah. So we can sort of, we can sort of prove it by argument. So if suppose that the array contains the largest element at a particular index, right? So the largest element is contained at index I, right?
So the largest element is already fixed.
Well, at the start.
So the element range is fixed. If so,
What do you mean?
Directly throw each element into each place.
Oh, so it's not fixed. This is just an.
Very fast.
Well, okay. So this is just an example, but the range of the numbers aren't fixed. They could be anything, but we're still guaranteed that the largest element will end up at the end of the array during the first pass, because every time we compare it to the next element, it's larger. So yeah, we swap it. Yeah.
You're right.
So here's the third pass. Right, so we compare 3 and 1. 3 and 1 are out of order, so we swap them. Then we compare 3 and 2. 3 and 2 are out of order, so we swap them. Then we compare 3 and 4. 3 and 4 are ordered, so we leave them. And we end up having the third largest element brought to the end. Right? Now here's the fourth pass. Right, so in the fourth pass, we compare 1 and 2. 1 and 2 are ordered, so we leave them alone. Then we compare 2 and 3. 2 and 3 are ordered, so we leave them alone. And that's the end of the pass, right? And since we haven't made any swaps during this pass, we stop, right? And we know that the array is ordered, right? So if the array was different, it might be possible that you need to make 5 passes, but in this case, we only needed 4 passes. Okay. So here is the implementation of bubble sort, right? So the outer for loop controls where each pass goes up to, right? So initially, the first pass is going to iterate all the way up to index high, right? The next pass, since we decrement I after completing a pass, right? The next pass is only going to go up to index high minus 1, right? And each pass is going to be shorter and shorter until the entire array is sorted, right? And before we begin a pass, we create a flag variable which allows us to keep track of whether an item has been swapped, right? So bool swapped equals false, and then this inner loop performs 1 pass down the array, right? So the pass goes from index low plus 1 up to index high, and then we compare the 2 adjacent items, right? So we compare index j with index j minus 1. If they're out of order, then we swap them, and we set the swapped variable to true. Right? At the end of the pass, if we haven't made any swaps, that means the array must be sorted, so we break. Yeah. Okay, so bool is a type similar to int that you can use if you hash include the stdbool.h header. It's nicer than saying int swapped equals 0 and then setting swapped to equal to 1, because it's clearer what the variable represents. It's a binary variable that's either true or false. Okay, so let's analyze bubble sort. So the best case is where the array is sorted, right? And you can imagine why that is. That's because we only need a single pass down the array, right? And in the first pass, we don't perform any swaps, right? So we stop right after completing the first pass. Right, so in total, we make n-1 comparisons, and we don't make any swaps. So the best case time complexity is O of n. Okay. All right, so what is the worst case? So the worst case is where the array is reverse sorted, right? And that's because we need to perform the maximum number of passes through the array. Right? So we need n-1 passes. Right, in the first pass, we need to perform n-1 comparisons, right, to go all the way down the array. In the second pass, we need to perform n-2 comparisons. Right, in the first pass, the 6 will be brought all the way to the end. In the second pass, the 5 is going to be brought all the way to the end after making n-2 comparisons. Then in the next pass, the 4 is going to be brought all the way to the end using n-3 comparisons, and so on, until the final pass, where we make 1 comparison. Right, so the total number of comparisons is therefore n minus 1 plus n minus 2 plus blah 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 plus 1, right? Which equals to this expression. So n times n minus 1 on 2. Right. And we also know that if the array is reverse sorted, then every comparison will lead to a swap, right? So we have the same number of swaps, and that means the worst case time complexity is O(n) squared. Okay? All right, so the average case time complexity is O(n) squared, right? And we can show this empirically by generating some random sequences and sorting them. So what I'll show you now is how we can do this. So I'm going to use the sequence command. So the sequence command generates a sequence of numbers from 1 up to whatever number you give it. And I'm going to take the output of the sequence command and feed it into the sort command. And I'm going to give sort an option which randomly sorts the input. Right? So you don't need to know these commands. I'm just showing you, how we can time bubble sort empirically. Right? And then I'm going to take that output and pipe it into the bubble sort program. Right? And bubble sort will happily sort the items. Right? So what I'm interested in is what happens when the input size gets really large. Right? So let me first test it with 10,000 items. All right, so what I'll do is I'll generate 10,000 items, then sort them randomly, then pass them into bubble sort. But I want to time how long the bubble sort program takes. Right, so I'm going to put time in front of the bubble sort command. Right, and if I run that, I'll get the numbers in order, and it also tells me how long the program took. Right, so if I sort 10,000 randomly sorted numbers, it takes about 0.24 seconds, right? 0.25 seconds. Right, and the output here is slightly different from the output I showed last Wednesday, because I'm using a Mac. All right. But the output you get contains the same information. So user time, system time, total, this is real time. All right, so 10,000 randomly sorted items takes about 0.24 seconds. Let's see what happens when I try to sort 20,000 items. Right, so let's see. Right, it takes about 0.95 seconds. Right, so it's about 4 times the amount of time it took to sort 10,000 numbers. Right, so around 0.95 seconds. And if we double it to 40,000, how long do you think it's going to take?
Times 4 again.
Yep, so about how long?
About 1.88 or 87.
Well, that would be doubling. So it take, well,
376.
yeah, it'll take about 4 seconds, right? A bit less than 4 seconds. So let's run the command again. Right, and we see that it does take about a bit less than 4 seconds. Okay. So yeah, so we can see that empirically, the average case of bubble sort is O(n) squared. Okay, so now for the properties. So bubble sort is stable, right? And the reason is we make comparisons between adjacent items only, right? And we only swap them if they're out of order, right? So if we have an array containing duplicates, right, then eventually the duplicates will end up next to each other, right? But we will never swap them because they're not out of order. Okay, so bubble sort is stable. Bubble sort is also adaptive, right? Because it's ON squared on average, but it's ON in the best case, right? If the input array is sorted. And bubble sort is in place, right? So the sorting is done within the original array, and it doesn't use temporary arrays. All right, so let's look at another algorithm, which is insertion sort. And now, insertion sort is it's inherently an adaptive sorting algorithm, and we'll explain how that's the case. Right, so how does insertion sort work? So insertion sort takes the first element, right, and treats it as a sorted array of length 1. Right, so we say that take the first element and treat that as a sorted array. Right, what happens next is we take the next element and insert it into the sorted part of the array so that the order is preserved. Right? And when we do that, that increases the length of the sorted part of the array by 1. Right? And we repeat this for the remaining elements. So I have an example here in case you're confused. So suppose we're sorting this array using insertion sort. Right? Insertion sort would treat the first element 4 as a sorted array. Right? Now we want to insert the 1. Right? So what's going to happen is we see that 1 is less than 4. Right? So we move the 4 along 1, so we shift the 4 down, and then we insert the 1 at the start of the array. Right? So that's what happens. Then when we insert the 7, we'll notice that 7 is greater than 4, right? So that means 7 is already in order with respect to the previous elements. Right? So we just leave the 7 where it is. Then when we insert the 3, we notice that 3 is smaller than 7, and it's smaller than 4, right? But it's not smaller than 1. So that means we would shift down the 7 and 4 and insert the 3 after the 1, right? Like that. Then when we insert the 8 just remains where it is because it's greater than 7. Right. Then when we insert the 6, we see that 6 is less than 8, and 6 is also less than 7, but it's not less than 4. So we put the 6 after the 4. Then when we insert the 5 is less than 8, less than 7, less than 6, and not less than 4. So we shift the 8, 7, and 6 down, and insert the 5 in between. Right? And then the 2 goes in between the 1 and the 3. Right? And that is insertion sort. All right, so yeah, and at the end, the array is sorted. Right, so here's the implementation of insertion sort. Right now, so what's going on here? So we see that the outer loop loops from low plus 1 to high, right? And it doesn't start from low. That's because we take the first element of the array, we take the first element as a sorted array, right? And then we insert the remaining elements. So we insert the element at index low plus 1, then low plus 2, then so on. And inside of this loop is where we perform the insertion, right? So we save the item at index I in a temporary variable, right? So for example here, when we're inserting 3, for example, we save 3 in a variable, right? Then inside this loop, we basically shift down elements until we reach an element which is less than the element that we're trying to insert. Right? So 3 is less than 7, so we shift the 7 down. Then 3 is less than 4, so we shift the 4 down. But 3 is not less than 1, so we insert the 3 here. Right? So, yeah.
How do you check the 3's place?
What do you mean?
How do you check where the 3's place is?
Right, so when we inserted 3, 3 is less than 7. Right, so we move the 7 down. Then 3 is less than 4, so we shift the 4 down. But 3 is not less than 1. Right?
So you're actually inserting 3 by the by bottom sort in different way.
Well, I wouldn't call it bubble sort. It's just insertion sort. So the thing with insertion sort.
Check the 3 place among the 1, 4, 7 by the binary search.
Well, you could do that. And that would be, if you use binary search, it would take log n to find out where the item should be inserted. But then the items would still have to be shifted, which would cost you O of n, yeah. Yeah, so one thing to notice here is that we're not really doing any swaps, right? We're just shifting the items down. And well, shifting is probably slightly faster, right? It's fewer instructions.
So those two are near is shift and far is swap.
Well, we'll see an algorithm next which actually does swap elements far apart. Yeah, so there's a question which is, why do we write this J in comments? So we're just writing this like this because we already initialized J to I in the line above, so we don't need to do it again. So we just comment it out and we write J here because J is the loop variable that we are using. Okay, so let's analyze insertion sort. Right, so insertion sort, the best case is when the array is sorted. Right, and the reason is that every time we insert an element, right, it takes only one comparison. Right, so for example, when we are inserting 2, right, we compare it with the 1, and 2 is greater than 1. So we just leave the 2 where it is. We don't need to compare the 2 with anything else. When we insert the 3, we compare the 3 with the 2, and since 3 is greater than 2, we leave it where it is. We don't have to compare the 3 with the 1. When we insert the 4, we compare the 4 with the 3, and 4 is greater than 3, so we leave the 4 where it is. And we don't need to compare it with 2 or 1. And the same thing for the remaining items. Right? So inserting each element requires only one comparison, and that's n minus 1 comparisons in total. Right. Did you have a question up in the back? Okay. Yeah. Yeah, we'll be getting to that. So yeah, the best case time complexity is ON. All right, so the worst case, right? So the array is reverse sorted, right? So why is that? That's because every time we insert an item, right, when we insert the ith element, that requires I comparisons, right? So consider this element here at index 1, right? In order to insert this, we perform one comparison with the 8, right? And then we shift the 8 along and then insert the 7 before. Right? When we insert the element 6, right, that requires 2 comparisons, right? So compare it with the 7 and 8. When we insert 5, we need to compare it with 3 elements, right? 6, 7, 8. And so the number of comparisons is 1 plus 2 plus blah, blah, blah plus n minus 1, right? Which is the same sum that we've seen a few times already, right? So n times n minus 1 on 2. Right, so the worst case time complexity is O of n squared. All right, and the average case time complexity is O(n) squared, and you can show this empirically by generating random sequences and sorting them. But I won't be doing that because I've already shown it for bubble sort. So you can do it for insertion sort if you're curious. All right, and the properties of insertion sort. So insertion sort is stable. right? And that's because when we're inserting, right, when we're looking back through the sorted part of the array, we stop when we find an item that's not, we stop when we find an item that is less than or equal to the item that we're trying to insert, right? So if we go back to here, suppose that the last item in this array was 8 instead of 2, right? So if it was an 8, then we would compare it with the item to the left, which is also 8, and we would just not shift the 8s down, right, because they're equal. Right, so we always insert elements to the right of any equal elements instead of inserting them to the left, right? If we did that, then it wouldn't be stable. Right, insertion sort is adaptive, so it's O(n) squared on average, but it's O(n) if the array is sorted. Okay, and insertion sort is in place, just like the previous algorithms that we looked at. Okay, so that's selection sort, bubble sort, and insertion sort. So we'll take a quick break. So we'll take a 8-minute break, and we'll come back at 3:10 to continue. All right, so let's continue our journey through sorting algorithms. All right, let's continue. So next up, we will be discussing shell sort. Right, so what is shell sort? Okay, let's keep going. So shell sort. Right, so what is the inspiration behind shell sort? Right, so first of all, we notice that bubble sort and insertion sort really only consider exchanges between adjacent elements. Right, so for example, if we go back to the insertion sort example, when we're trying to insert 2 here, right, we needed to shift everything, shift all of these elements down and then insert 2 near the beginning. Right, so that's a very long distance for the 2 to move, right? And it takes a lot of shifts. So the question is, if we make longer distance exchanges, so exchanges between elements which are further away from each other instead of just adjacent elements, can we be more efficient? Right, so what if we consider elements that are some distance apart from each other? And that's the inspiration behind shell sort. So shell sort, it's named shell sort because it was invented by Donald Shell. Just a little bit of trivia. All right, so what is the idea behind shell sort? Well, an array is, so first we have to introduce the idea of H-sortedness. Right, so an array is H-sorted if taking every H element yields a sorted array. Right, and I'll show you an example of that just after this, if you're confused. And we notice that an H-sorted array is made up of n divided by H interleaved sorted arrays. Right, and the idea behind shell sort is to H-sort the array for first a large value of H, right, and then we progressively reduce H until H is equal to 1. And once H is equal to 1, that's the same as performing an insertion sort on the array. Right, so first of all, let me explain what it means for an array to be H-sorted. Right, so here are some examples of H-sorted arrays. Right, so here we have a 3-sorted array. And what this means is that if you take the groups of elements that are multiples of 3 indexes apart, right, then those elements will be sorted with respect to each other. All right, so for example, I've colored the groups in different colors, so we can see that one group of elements is index 0, 3, 6, and 9. Right, so the elements are 4, 5, 7, and 8, and these elements are sorted with respect to each other. Another group is index 1, 4, and 7, right? And the elements at these indexes are 1, 3, and 6, so these elements are sorted. And the last group is indexes 2, 5, and 8, right? So the elements at these indexes are 0, 2, and 9, so these are also sorted, right? So that's an example of a 3-sorted array. Here's an example of a 2-sorted array. Right, so in a 2-sorted array, each group of items that are 2 indexes apart or a multiple of 2 indexes apart are sorted. Right, so if we look at the even index items, so these items are 1, 3, 4, 7, and 9, so these are sorted. If we look at the odd numbered indexes, the items at these indexes are 0, 2, 5, 6, and 8, and these items are also sorted. Now, what is a 1-sorted array? Well, 1-sorted array is just a sorted array. Okay, so here's an example of shell sort. Right, and what shell sort actually uses to sort these groups of elements that are multiples of H apart is it uses insertion sort. Right? It uses a generalization of insertion sort. Right? So what we'll do here is we'll first 3 sort the array. Right? So we'll H sort the array where H is equal to 3. And we'll sort each group of items that are multiples of 3 indexes apart. Right? So the first group is 4, 3, and 5. Right? And what we do is we sort these elements using insertion sort. Right? So once we sort them using insertion sort, we get 3, 4, and 5. Right? Then the next group of elements is indexes 1, 4, and 7. Right? And the items are 1, 8, and 2. So if we sort these, we get 1, 2, and 8. Okay? Then the last group is index 2 and 5. So if we sort these, we get 6 and 7. Right? So after we've done this, the array is now 3 sorted. Right? So that means if you take the groups of elements that are multiples of 3 apart, then those groups are sorted, right, with respect to the elements within them. All right, so we've 3 sorted the array. Now let's try 2 sorting the array. Right, so if we 2 sort the array, that means we're sorting all the even numbered indexes. Right, so the even numbered indexes are 0, 2, 4, and 6. The elements are 3, 6, 2, and 5. Right, so if we sort these elements, we get 2, 3, 5, 6. Right. Then we sort the odd numbered indexes. So these elements are 1, 4, 7, and 8. And it turns out that these elements are already sorted. Right. So the result is just 1, 4, 7, and 8. Right, so now the array is 2 sorted. Right, and finally, we perform one pass where H is equal to 1. Right, so when we 1 sort the array, that's the same as performing insertion sort. Right, so we perform insertion sort, and the array is sorted. Right, yes. Yeah, so the question was, does the value of H depend on the size of the array? Yes, it does. So if the array is larger, then we will start with a larger value of H. Yeah, so remember the goal of shell sort is to try to minimize the number of long distance swaps that we have to do, right? The number of swaps. So yes. Question.
If the length is n, so what's the h should be chosen at the beginning?
That's a good question. So what h should we choose? And it turns out that there are lots of different possible sequences.
A root or like h equals to n by 2?
So it depends on the sequence, and if you go to the Wikipedia page on shell sort, there are a bunch of different gap sequences, and each of those sequences leads to a different time complexity. All right. So here's the implementation of shell sort. Don't worry, you don't have to know how to implement this, but the first part of this function finds an appropriate h value. Right. So the larger the size of the array, the larger the h value that you start with. And then we have a for loop here, which gradually reduces the value of h. Right? So first we h sort with a large value of h, then we reduce that, and then h sort with a smaller value. Yes, question. These are not in the C standard library. So, we would never ask you to use shell sort though in the course. This is just another sorting algorithm. So none of these are in the standard library. Unfortunately, that's C. But yeah. So this outer loop just reduces the value of h gradually until it's 1. And this inner loop essentially performs insertion sort, right? Except with insertion sort, we were comparing, JSON elements, but in shell sort, we are comparing, so we're comparing with index j minus h, right? So that's because we're h sorting the array. Okay. All right, so onto the analysis. Now, shell sort doesn't actually have a general analysis, right? So the efficiency of shell sort, the time complexity, depends on the h sequence, right? Depends on the sequence of h values that you use. And so good h sequences have been determined empirically, right? And many h sequences have been found to be O of n to the power of 3 on 2. So here's one of them. And some have been found to be O of n to the 4 on 3. Right, so yes. We don't know. That's the thing. Yeah, we don't know the answer to that. So there hasn't been like a full analysis of shell sort, really. So we don't really know if this time complexity can be improved. But these are just some results that have been found empirically. All right. Yeah, and if you go to the Wikipedia page on shell sort, you can find sequences with these time complexities. All right, so what are the properties of shell sort? Right, so shell sort is unstable, right? That's because we perform long distance swaps. Right? Shell sort is adaptive, and that's because it uses a generalization of insertion sort, which is adaptive. All right? And shell sort is in place, so sorting is done within the original array, and it doesn't use temporary arrays. All right, so these are all of the elementary, inefficient sorting algorithms that I wanted to cover. Right, so selection sort, bubble sort, insertion sort, and shell sort. This is just a summary of the sorts. All right, so you can have a look at this. So this table might come in handy. Depends on the H sequence. That's what it means. Yeah. Yep.
Why does it mean it's unstable?
So shell sort is unstable because we perform long distance swaps. So we swap items which are far apart from each other.
So that is unstable?
Yeah, so it's unstable.
And what about what's another word? Stable and adaptive.
Yeah.
What does adaptive mean?
Adaptive.
Not adaptive.
Sorry?
Why the first one is not adaptive?
The first one, selection sort.
Yeah.
Well, I already explained that earlier, but it's not adaptive because it performs the same steps regardless of how sorted the original array is. Well, it's not adaptive because it performs the same steps regardless of how the original array is sorted. You can go back and have a look at the slide. All right? All right, so the focus of the lecture is sorting arrays, but you can also sort linked lists, right? So with selection sort, you can sort it. You can sort a linked list by doing this. So you let L be your original list. You let S be your sorted list, which is initially empty, and then repeatedly you take the largest element from the original list and remove it and insert it at the start of the sorted list. Right? And if you keep doing this, you will end up with a sorted array. Right, so that follows the kind of method of selection sort. Right, with bubble sort is fairly simple to implement. When you're sorting a linked list, you just traverse the list and you just compare adjacent values. If they're out of order, then you swap them. All right, and insertion sort. So you can also sort linked lists using insertion sort. So for each node in the original list, you just insert it into a new list in order. Right, so it's like applying that insert ordered function that you wrote in lab 1, right? And so you loop through the original list and you just call that function for every value in the list. All right, now how about shell sort? Well, shell sort is difficult to implement if you're sorting a linked list, right? And that's because in shell sort, when you're at index j, for example, you might have to find index j minus h, right? And if you have a linked list, it's hard to access a specific index in constant time, right? Because you have to traverse from the beginning. So shell sort's hard to implement when you're sorting a linked list. All right, so there's feedback if you want to give feedback. And that is it for basic sorting algorithms. So now we're going to continue on and talk about a more efficient sorting algorithm. Yes, question. Sorry? Do you need to know, sorry? How to apply shell sort? Probably not in the course. You should know the properties of shell sort, but I don't think you need to know how to use it. Yeah, question? Your question was, aren't selection sort and bubble sort? Selection sort and bubble sort. So, yes, bubble sort and insertion sort are very similar in terms of their time complexity and properties. Yes, but there are differences. There are some differences. Yeah. All right, so yeah, now we'll have a look at merge sort. Right, so merge sort is what we call a divide and conquer algorithm. Right, sounds cool, right? So what is a divide and conquer algorithm? So it's an algorithm that splits a problem into smaller subproblems of the same type, and then it solves the subproblems recursively, right? And then combines the results, right? So sounds a little bit like recursion, right? Except with divide and conquer algorithms, we're usually splitting the problem into 2 or more subproblems. Okay. All right, so in what way is merge sort a divide and conquer algorithm? Well, how it works is we split the array into 2 roughly equal-sized parts, right? So we essentially find the midpoint and then we split the array at that point. And then we recursively merge sort each of the halves. Okay, so we sort each of the partitions, and once both of these halves are sorted, we merge them into a sorted array. All right, so here's a diagram that shows that. So we have 2 unsorted halves of the array. We recursively merge sort each half so that both halves are now sorted. Then we merge them together into a full sorted array. All right, so here's a nice diagram actually showing how merge sort splits the arrays and merges them. All right, so at the beginning, we have an array of size 8. Right, so what merge sort will do is it will split the array into 2 halves, right, of size 4, right, and then recursively merge sort each half. Right. Well, let's focus on this half. So how do we merge sort this half? Well, once again, we split it into two halves, right, each containing two elements, and then we recursively merge sort each half, right? Well, let's focus on this array. So how do we merge sort this array with 5 and 2? Well, once again, we recursively, we split it into two halves, right? Each half containing one element, and then we recursively merge sort both of them. And how do we merge sort an array containing a single value? Well, that's the base case of the sort. That's the base case of the algorithm, right? So when we have one element in the array, then we don't need to do anything to sort the array, right? So that's the base case, and we just return, right? And here is where we merge the sorted subarrays into a single subarray, right? Into a single array. So we have 5 and 2, we merge those to get 2, 5. 4 and 7, we merge those to get 4 and 7. And now we have two subarrays of size 2. So now we merge those to get 2, 4, 5, 7. And once we have two sorted subarrays of size 4, we merge those into a single subarray, into a single sorted array of size 8. Question? I'll show you how we merge the two arrays, in a bit. So you might be wondering, so how do we actually split the array and how do we merge the arrays? Right, so when we split the array, we aren't actually physically splitting the array. What we're actually doing is we just calculate the midpoint of the array, right? So mid equals low plus high divided by 2. And then we just call the function with appropriate indexes so that it seems like we're merge sorting each half, right? So we just call the sorting function recursively with indexes low and mid, right? So this sorts the left half, and then we recursively sort between indexes mid plus 1 and high, right? So that sorts the right half, right? So that's what it means to split. So we just calculate the midpoint and then call the function recursively on both halves, right? And this means the time complexity of splitting is actually just 0.1, okay? So there's actually not much work done when splitting. So merging is the hard part, right? So we have two subarrays of roughly equal sizes, and they're both sorted. Right? So how do we combine them into a single sorted array? Well, here are the main points. So first of all, we use a temporary array. Okay, so it's not possible to do it within the original arrays. We have to use a temporary array. And what we do is we keep track of the smallest elements that hasn't been merged in each subarray, and I'll show you a visualization of that. And while we're keeping track of the smallest element that hasn't been merged yet, we take the smaller of the two and then copy it into the temporary array, okay? And if the elements are equal, then we take from the left subarray. And I'll also show that in the example. Right? And then we just repeat until all elements have been merged. All right? And then we copy from the temporary array back into the original array. All right, so here is my example. Right, so here I have two sorted subarrays of size 4, right, one here and one here. The reason I glued them together is that in reality they are right next to each other, right? When the merge sort function is actually running, they are right next to each other. So what we do is we compare the smallest element from each half, right? So 2 and 1, and the 1 is smaller, right? So we copy the 1 into the temporary array, and we have some indexes here to keep track of where we're up to in each array, right? So we have one index that points to the first half, another index that points to the second half, and another index into the temporary array to keep track of where the next element should go. All right? So now we've inserted the 1. So now we want to insert the next element. Right? So in the left half, we have a 2, and in the right half, we also have a 2. Right? So when we have equal elements, we take from the left half, right, from the left subarray, and this will ensure stability. All right? So we take the 2 from the left and copy it down. Right, now we are comparing 4 and 2. Right, so the 2 is smaller, so we copy that down. Now we're comparing 4 and 3. So 3 is smaller, so we copy that down. Now we're comparing 4 and 6. So 4 is smaller, so we copy that down. Now we compare 5 and 6. 5 is smaller, so we copy that down. Now we're comparing 7 and 6. And 6 is smaller, so we copy that down. And now we've run out of elements in the right subarray, right? So once we run out of elements in one of the subarrays, we can simply copy the remaining elements from the other subarray, right? So we just copy the 7 down, and we're done. Right? Except you have to copy all the elements back into the original array. Okay, so that's one example. Here is another example, just to show you that the exact same thing applies to much smaller arrays. Right, so we have 2 subarrays, 2 sorted subarrays of size 1. So what do? Well, we compare 5 and 2. 2 is smaller, so we copy it down. Now we've run out of elements in the second half, so we just copy the 5 from the first half down, and then we just copy it back to the original array. All right, so yeah, that's how merging works. Right, and there is a much more, there's a much fuller explanation in the appendix if you are interested. All right, so how efficient is merging? Right, well, the time complexity of merging 2 sorted subarrays is O(n), where n is the total number of elements in both subarrays. Right? And the reason is that we are making approximately n comparisons. Right? So if we go back to the beginning of this example, we're comparing 2 and 1. Right? Then we are comparing 2 and 2. Then we are comparing 2 and 4. So we're making one comparison for each element approximately. Right? One comparison for each element in the array. So it takes about n steps to merge 2 sorted subarrays. Yes?
So the area complexity is Q n log n, right?
So we'll get to memory usage later. Yeah, I'll explain that later. It's coming, don't worry. Yeah, so the time complexity of merging 2 sorted subarrays is O(n), where n is the total number of elements. And therefore, if we have 2 sorted subarrays of size 1, right, merging those takes approximately 2 steps. Right? So I'm saying steps in quotes because it's not 2 operations, it's more like 2 times k operations, where k is a constant. Okay? Then, when we merge 2 subarrays of size 2, that takes approximately 4 steps. Right? Then, when we merge 2 subarrays of size 4, that takes approximately 8 steps, and so on. So this will be important later when we do analysis. Okay, so here's the implementation of merge sort. Right, this isn't the whole thing, this is just the merge sort function. And notice how simple this function is. Right? All we're doing here is we're just checking the base case. Right? If the array has only 1 element, then we return. Otherwise, we calculate the midpoint, then we recursively merge sort each half of the array. Right? Then we merge the 2 halves together. So now you ask, how does the merge function work? Well, here is the merge function. Right? So the merge function is where the bulk of the work happens in merge sort. Right, so first we allocate a temporary array, because remember that in order to merge we need a temporary array. Then we initialize a bunch of indexes. Right? Remember when I showed you the visualization, we needed some indexes to keep track of where we were up to. Then this first while loop, so that does the comparison between elements and taking the smallest element and copying it down, right? And then after that, we have two while loops just to copy the remaining items from the half that, well, if we run out of elements from one half, then we need to copy the elements from the other half, right? So these two while loops are just responsible for that. And then we need to copy the items back into the original array, right? So this for loop just does that. Right, then we free our temporary array. All right, so now let's analyze merge sort. Right, and to analyze it, I just want to bring back this diagram because it's nice. So what happens in merge sort? Well, we perform splitting and we perform merging. Right, so first of all, how many times do we have to split? Right, well, if you count the number of splits, it turns out that we have to do n-1 splits in total, right? So, for example, this array of 8 elements, we can count how many splits we have to do here, right? 1, 2, 3, 4, 5, 6, 7. Right, that's 7 splits. And so the total cost of splitting, since splitting costs O1 and we have n-1 splits, the time complexity of the splitting part is O of n, right? Because we perform about n splits. But the important thing to notice is that there are log 2n levels of splitting, right? If you count how many levels there are in this diagram when we split, there are about log base 2n levels, right? And the reason is every time we split, we're halving the size of the subarray, right? And think back to binary search, how many times can you halve the size of the array before you reach just individual items? That's log base 2n, right? So you have log base 2n levels of splitting. And that means when we merge, right, we also have approximately log base 2n levels of merging, right? And that is where the log n comes from in this n log n. Now, where does the n come from? Right? Well, if we look across each level of merging, right? Let's look at the first level here, where we have individual items, right? In order to merge these two items into a single array of size 2, that costs about 2 steps, right? To merge these two, 4 and 7, that also takes about 2 steps, and to merge the 1 and 3, that takes about 2 steps, and to merge the 2 and 6, that takes about 2 steps, right? So across the entire level, we perform about 8 steps, right, in order to merge all these elements into sorted subarrays. Right? In the next level, right, merging 2 subarrays of size 2 into a subarray of size 4, that takes about 4 operations, right? And then merging these 2 subarrays also takes about 4 operations. So across that level, it also takes about 8 steps, right? 8 operations, right? So for each level of merging, we're performing about 8 steps, right? Or 8 operations. And therefore, because we have log base 2n number of levels, that means we have to perform about n times log n number of steps, right, to complete the merging. Okay, so yeah, sort of reflects the fact that merging is where, merging is where the most of the work happens, right? Okay, so here is basically what I just said. So merge sort splits the array into equally sized partitions. So that means we have log base 2n levels. And each level requires about n comparisons in order to merge. Okay, so therefore the time complexity of merge sort is O n log n. Right, and the best case, average case, and worst case time complexities are all the same. All right, and that says something about whether merge sort is deductive or not. Okay, so here is another method of analyzing that you might learn in COMP2521 if you do that, but you don't need to know it for this course. Right, so yeah, in order to analyze divide and conquer recursive algorithms, you can use something called the master theorem, right? And you'll learn that in COMP2521. Sounds cool, right? But yeah, you don't need to know this. All right, so what are the properties of merge sort? Well, merge sort is stable, right? So I explained why it's stable, because when we are merging and we have two equal items, we take from the left subarray. Right? That guarantees stability. All right, merge sort is non-adaptive. Right? That's because it is O n log n in all cases. And merge sort is not in place. Okay, so we need a temporary array of size up to n. Right? The final merge is going to require a temporary array of size n. Right? And another note is that merge sort also uses stack space, right? Because it's a recursive algorithm. Right? Remember when we talked about recursion last week, every time a function is called, a stack frame is created for it. So since merge sort is recursive, it uses stack space and specifically uses log n amount of stack space. Right? All right, so now, is it possible for us to merge sort linked lists? So yes, it is. But we're not going to go into the details of it. But what you would do is you would split the list into two halves, right? And then you would recursively merge sort each half. And then once you have the two sorted lists, you would merge them together into a single sorted list. Right? And the merging the two sorted lists is actually a nice programming exercise if you want extra practice with linked lists. Right? Merging two sorted lists. All right, so, okay, something else. So merge sort is normally a recursive algorithm, right? But it turns out there is a way to implement it non-recursively. And I think it's best if I actually show you the diagram straight up. Okay, so this is called bottom-up merge sort. And how it works is that we suppose that our array has a bunch of sequences, a bunch of sorted sequences of length 1. Right? So in this array of 16 items, each of these elements is a sorted array of size 1. Right? Then what we do is we take two elements at a time and then sort those. So we create sorted subarrays of size 2 by taking two elements at a time. So for example, the first two elements are A and S, so we sort those. The next two elements are O and R, so we sort those. The next two elements are T and I, so we sort those. So that becomes I and T. So now we have sorted runs of length 2. Right? So after we have these runs of length 2, we can now merge them into runs of length 4, right? So we take these 4 elements and we merge those into AORS. Then we take the next group of elements and combine those into GINT and so on. Right? Then we combine, then we merge those into runs of length 8, then we merge those into runs of length, or into runs of length 16, which is the entire array. All right, and here is the implementation of that. Now, let's look at what's going on here. So this for loop, right? So this for loop controls the length of the runs, right? So initially, we start off with runs of length 1. That's why m begins at 1. And every iteration, we double it, right? So we double it, m times equals 2, right? So in the next iteration, we have runs of length 2. Then in the next iteration, we compute sorted runs of length 4. And then in the next iteration, we compute sorted runs of length 8, and so on. Okay, and this for loop, this inner loop here, so this is responsible for going through the array and actually merging every two groups of runs. And so we take the first two sorted groups, and then we call the merge function. Then this loop moves on to the next group of sorted runs and merges those, and so on. And the merge function here is the same as the merge function from the merge sort that we looked at earlier. Yes?
So it doesn't create stack.
So yes, so this function, it only calls one function, which is merge, and that's it. The merge sort that we looked at earlier, so this is the standard merge sort, it can recurse on itself about log n times. Yeah. So this function would use less stack space, but it does still use a temporary array. Right? Yeah, because, sorry? Sorry? Yes, the runtime would be similar, yeah. Okay, and in the appendix, we have a longer example of merge sort in case you want to have a look at it, but that is all the content for today. So yeah, I'll see you guys on Wednesday for more sorting algorithms.